So let's look at the first example. Find VO in the network using mesh analysis. So step 1, we're going to define the loop or mesh current. So this is my first mesh current, and this is my second mesh current, and this will be my third mesh current. Second step is to write the loop equations. For the first loop, we count the voltage drop one by one. So 1 plus 1 times I1. At the same time, we have a minus I2 times 1, right? Minus I2 times 1. At the same time, there is a voltage drop, which is 6 plus 6, that is equal to 0. So this is how we find the first loop equation. The second loop, we do the same thing. The coefficient for I2, that is 1 plus 1. Then minus the shared resistance I1 times I1 minus this 1K times I3 minus 12 is equal to 0. For the third mesh, the coefficient for I3, which is 1 plus 2 times I3 minus the shared resistance between 2 and 3, that is 1K, minus I2 times this 1K, right? I2 times 1K. And there is a voltage drop of negative 6 by following the direction of I3. So minus 6, that is equal to 0. So this is how we write the three equations. Step 3, solve equations. And we'll simplify them a little bit. The first equation, that is 2 times I1 minus I2 is equal to negative 6. And the second equation, 2 times I2 minus I1 minus I3, that is equal to 12. And the third equation, 3 times I3 minus I2, that is equal to 6. So from the first equation, we can find I2 in terms of I1. So I2, that is equal to 2I1 plus 6. So we plug this back into the second equation. So replace I2 by 2I1 plus 6. And from the last equation, we find a relationship between I2 and I3. And we replace I2 by I3. So I2, that is equal to 3I3 minus 6. So we can further replace I2 by I1. I3 will be equal to 1/3 of I2 plus 2. And I2 is equal to 2I1 plus 6. So that will be 2/3 of I1. So we find I1, and we can find I2 and I3. So I2 is equal to 2 times of that plus 6. So that is 24 plus 42. So that will be 66 over 7. And I3, that is equal to 36 over 7. So this is the first method. This is also the general method that how we solve this problem. But if we look closely, we find this problem only have voltage sources. We can do model by inspection. Second method is called model by inspection. If we do model by inspection, we can define the mesh current in the same way. So step 1, we define the mesh current. Then step 2, we'll write the loop equations. So over there, we're going to write it in terms of equation set. And in this equation set, will be something matrix times unknowns, that is equal to the other side. The unknowns, we have 3. We have I1, I2, and I3. And on the right-hand side, which is the voltage increase. So following the first loop, we have a negative 6. In the second loop, that is a 12 because it's an increase, right? And in the third loop, we have an increase of 6, so that is 6. And in this matrix, the 3 by 3 matrix, the diagonal entities are summation of the resistance in the loop. So for the first loop, which is summation, which is 1 plus 1, that is 2. And for the second element, which is 1 plus 1, that is 2. And for the third loop, we have 1 plus 2, that is 3. The off-diagonal entities are shared resistance between the meshes. Between mesh 1 and 2, we have 1, so which is why we should negative 1. And between 1 and 3, there's nothing, so that is 0. Between 2 and 3, there is a shared resistance 1K, so this is why we have negative 1 there. And since this matrix is symmetric, we'll just put everything else there. Negative 1, 0, and this is a negative 1. So this is how we do model by inspection. Then we solve this matrix form, we'll be able to find the same answer. So in this example, we're going to find a VO in the network using loop analysis. VO is given here. The first step for loop analysis is always to define the loop currents. How do we define loop currents? So the most obvious way is to define the mesh currents. And by looking at this problem, we see two independent current sources. So it is case 2 of the 4 cases that we talked about on Monday. So this is case number 2. So it's good to have unshared current sources. So if we define the loop currents like this, say this is my loop current 1, let's define it in the other direction because I want to make this I1 to be positive number. So if I define it this way, it means I1 is equal to -4, right? I don't really like negative numbers, so I want to define I1 in the other direction. We also said that it's better to define all these current in the same direction. And the same direction means either clockwise direction or counterclockwise direction for all the loop currents. If that is my I1, I will define this as my current I2. And similarly, we'll define this one as I3, and this will be my I4. So the second step is to write loop equations. So all the loop equations are written by using KVL. So the loop equation means that you follow a loop to write a KVL equation. So for the first loop, the current in this branch is purely defined by the current in this mesh. So there's only one mesh current going through this branch. So this is why I1 is equal to 4 milliamp. And similarly for current I2, that is 6 milliamp. And for the mesh I3, we need to write the KVL equation. So the way to write it is to count the voltage drop by using Ohm's law. So the voltage drop on this 1K resistor, that is I3 minus I2 times 1. And the voltage drop on this 1K resistor is 1K times I3 minus I4. And the voltage drop on this 2K resistor, that is I3 times 2, because there is only one mesh current going through this branch. So the current going through this branch is I3. And there is also another more direct way to write the equation. We know that the loop equation for this mesh, the coefficient for I3 is equal to the summation of the resistance of all these resistors in this mesh minus the neighboring loop currents times the resistance shared with this mesh. So the coefficient for I3 is equal to the summation of all. So it's 1 plus 1 plus 2. And the coefficient for I2, which have a shared resistor with I3, so that is minus 1 times I2. And the other one is this resistor shared between I3 and I4, so we use the minus I4 times 1. That is equal to 0. The next loop equation is about this loop. So we do the same thing, count the voltage drop. The voltage drop on this 2K resistor, which is I4 minus I1 times 2. The voltage drop through this power source is 6, and the voltage drop on this 1K resistor is I4 minus I3 times 1. So the coefficient for I4 is the summation of all the resistors in that mesh. So that is 2 plus 1. And there is a shared resistor between mesh 4 and mesh 1, so that is 2 times I1. There is also another shared resistor between loop 4 and 3. So we have a minus I3 times 1. And don't forget this voltage source. There is a voltage drop on this voltage source by following this direction.
Minus 6, right? Oh no, plus 6.
That is a plus 6 because the direction is this way from the higher to the lower. So this is a down 6 volts. So plus 6. So that is how we get these 4 equations. The next step is to solve the equations. So step 3, we're going to solve equations. So since this problem you already know the I1 and I2, so you basically just submit those numbers into the following 2 equations. So that will give us, this is minus 6. So if we put it to the right hand side, it becomes 6, right? And I1 is equal to 4, so this is minus 8. So we replace this with a minus 8 plus 6, that is minus 2. And we put 2 to the right hand side, that will give us 2. By comparing these 2 equations, if we multiply the first equation by 3 and add to the second equation, that will help us to find I3. So that is 11 I3. That is equal to the right hand side, 3 times 6, 18 plus 2, that is 20. So that is how we find I3. It's a 20 over 11. Then we can find I4. We can find I4 from this equation. I4 is equal to 4 times I3 minus 6. So 4 times that, the numerator will be 80. 80 minus 66, that is 14. So we have 14 over 11 milliamp. So this is how we find all these loop currents. After we find all these loop currents, the next step is to give the conclusion. So this problem is not looking for the loop current. We are looking for the voltage VO. VO is over here. VO is the voltage drop on this 2K resistor. By following the passive sign convention, the voltage drop using Ohm's law can be defined as the current going through this branch times the resistance. The current has to be from the left to the right. So that is I1 minus I2. I1 minus I2, negative 2. So that is a negative 4 volts. So if you look back from this problem, actually you don't need to solve I3 and I4 to get the final answer for this problem, right? Because this problem, if we're looking for VO, we only need I1 and I2. So I1 and I2, that's a given. So if you can see that from the very beginning, and you don't need to go through all these calculations, then you can find a VO. But that will lose the purpose for us to do the practice though. Since we are at the beginning of learning this, so this is why we go through all the steps to show you how we are going to solve the problem. By giving all this loop current, you can find anything in the circuit. For example, in the exam, if I ask you to find the voltage drop on this 1K resistor, and you should be able to do that. In that case, you will need I3 and I4. I can also simply ask you to find a voltage drop on this 2K resistor or on this 1K resistor, right? So giving you the same circuit, there are many other different things I can ask you to find out. I can also ask you to find the current going through this branch. If I ask you the current going through this branch from the left to the right, it will be I1 minus I2. If I ask you the current going through this branch from the right to the left, then it will be I2 minus I1. Next question. In this example, we're going to look for current I0 in the network. The current I0 is over here. By looking at the problem, we have both voltage source and a current source. And this current source is a shared source between two different meshes. It means that it's a case 3. So the case 3, that's the case where we have shared current sources. In that case, we have different methods to solve this problem. You can either use the Supermesh method or use the general loop method. So in this problem, we're going to use both of two different methods to solve this, and you will see the difference. Alright, so let's first use the Supermesh method. Method 1, Supermesh method. In Supermesh method, we define the mesh current as usual, as how we do for the other problems. For example, we can define our mesh currents like this. Let's start from here then. So mesh 1, mesh 2, and mesh 3. Step 1, define mesh currents. We already did that. You can also say define loop currents because mesh are special loops. The second step is to write the loop equations. And whenever we have a shared current source, we know that that will give us one constraint. We want to be able to write two equations from these two meshes. So that will give us one constraint. For the first mesh, there is no problem. So we can write this first equation as a usual by using KVL. So the coefficient for I1, that is a 3 plus 2. Can I write it directly as a 5? Or you want me to write it in details, like then we simplify it? So if you're not sure, we'll write it in details. So at least when you review the video, you know how I got a 5. So let me do that then. And at the same time, this resistor is shared between mesh 1 and 2. So we have a minus 2 times I2. And there is also a voltage drop by following this direction plus 12, that is equal to 0. So this is the first mesh, no problem here. Between the second mesh and the third mesh, you cannot write the KVL equation because you won't be able to know the voltage drop on this current source. That is why we cannot write an equation like that. Instead of having the KVL equation, we will be able to find a constraint between 2 and 3. The constraint is given by this current source. This current source tells us that no matter what, the current going through this branch has to be 4 milliamp. So the current going through this branch, if we write it in terms of the loop currents, it will be I3 minus I2. So this is why it gives us I3 minus I2 is equal to 4 milliamp. So now you see we only have two equations. And we need a third equation so that we can solve for all three unknowns. In that case, we need to define a supermesh. How do we get this supermesh? The way to get supermesh is to assume that this current source is not there. Say, assume that this doesn't exist. Then we'll be able to see another mesh. This is one mesh now in that case. So that is how we define the supermesh. So I'm going to define my supermesh like that. I'm going to give it a different color. So that is my supermesh. I'm going to write a third equation by using KVL by following this supermesh. Although we use this supermesh, we still need to use our defined mesh currents. So the voltage drop on this 1K and 2K is calculated by using I3 times the resistance. So we have a 2 plus 1 times I3. The voltage drop on this 3K resistor is current I2, right? So we have a plus 3 times current I2. The voltage drop on this 2K resistor that can be calculated.
Plus 2K times I2 minus I1?
Yes. The current going through this branch is I2 in this direction, the same as the super mesh current direction that we are following, right? So that is I2 minus I1. I think we counted everything, so that will give us 0. So this is how we get the three equations. And the next step is to solve these equations. I'm going to let you practice how to solve these equations. Tell me the answer after you're done. So I'm not sure whether I get the same answer as you or not. What I have, I1 is equal to negative 10 over 3. I2 is negative 7 over 3. I3 is 5 over 3 milliamp. Do you get the same answer? Last step 4, conclusions. In this problem, we are looking for I0. I0 is over here. We know that I0 is the current going through this branch, which is equal to loop current I2 minus I1. So that is this is 1 milliamp. So this is how we solve this problem. The second method called the general loop method. So in the general loop method, the first step is the same, but you cannot no longer call it a mesh current because we're going to define a loop current. So the way that we're going to define the current will be different. So since we know that if we define the current like what we did before, and this over here we only give one equation. So I don't want to define I3 like that. I want to define my I3 in a different way. So that will lead us to define a loop current. You can find this loop by using a similar way of finding the supermesh. It is fine, but this is not unique. You can have another loop. It goes from everywhere. You can do it from here, here, everywhere. You can define that loop 3 that way. So this is how we define the 3 loop currents. And the second step is the same. We write loop equations. For the first loop, will it be different or the same? What do you think?
The same.
The same? Any other opinions? How many currents going through this branch?
2.
I1,
3.
I2, and I3. What's in the previous problem? It has I1 and I2. So the problem is different now. So the first equation is also different. That is something we need to pay attention to. So right now, my current equation for the first loop is different because I have I3 shared with this as well in this branch. If you are not familiar with this way to write the equation, I would encourage you to write it element by element. Don't write it like this. Because the way that I write it, I already see all the connections. So if you are not sure, I would still encourage you to write the equation element by element. The voltage drop on this element, the voltage drop on that element, the voltage drop on this resistor. You combine all this together to write the equation. So what I have here, because I know that the voltage drop, that will be the drop shared by this I1, which is 2 plus 3. The voltage drop due to I2 because it's in the reverse direction of I1, so that is a minus 2 times I2. And there is also another shared current. It's in the reverse direction of I1, so we have a minus 2 times I3. And then plus this voltage drop 12, that is equal to 0. This is our first equation. How about the second equation? The second equation is also different from this. right now there's no shared, this branch, there's only one mesh current going through this branch in this case. This is why current I2 is equal to -4. And the third equation is about this general loop. So write the voltage drop on this general loop. Remember, it's also different from this equation. So let's count the voltage drop. The voltage drop due to I3, that is a 3 plus 2 plus 1. The voltage drop due to the current I2, that is a 3, 2. And they are in the same direction, right? And anything else? There is another one here. So this we have a -2 times I1, that is equal to 0. So this is how we get all the three equations. The next step is to solve all the three equations. Do you think the answer will be the same?
Should be, right?
Yes.
You think the same? And how about I2? The final answer should be the same. The conclusion should be the same. I'm asking whether I1, I2, and I3 will be the same as this I1, I2,
Oh,
and
no,
I3.
no.
I1 can be the same, right?
No, because there's I2 and I3 and I1, right? There is no.
No?
Wait, I1 would be the same? Yeah, I1 would be the same, and I3 and
But I3 and I2 are different.
Yeah, that's a good guess. So I1 should be the same because the current going through this 3K resistor, I'm talking about the actual current, should be unique. So this is why I1 is equal to the actual current going through this 3K resistor. This I1 is also equal to the actual current going through this 3K resistor. This is why I1 has to be the same. And I2, I already have it. It's here. And how about I3? What do you think I3 will be? Is I3 the same as this I3?
No, it's different.
Why?
It's plus I2, maybe.
Look, what is the actual current going through this 1K resistor in this circuit?
Little I3.
I3, right? How about the actual current going through this 1K resistor?
No extra current.
The same.
The same, right? Look, there is only one loop current going through this branch, and which is I3. And this is how I define I3. And I3 is also the same as the previous solution. So only I2 is different because the way how we define it, right? So how do you think about the final answer now? Is the final answer the same? It should be, right? Otherwise we will have mistake. So what is I0 in this case? So let's take a look at the circuit over here. I0 is equal to the combination of all these three mesh currents now. So we have I1 going through the reverse direction, right? So that is negative I1.
I3 minus I1.
And we have I2 is in the same direction, right? And how about I3?
Plus I3.
Plus I3. Perfect. So that's how we get it. If you are not confident about the final answer at 1 milliamp, let's do a verification. So it is equal to this, plus this, minus that. This is a negative 12 plus 5, that is a negative 7, so which is equal to the previous I2, then minus I1, so that is equal to 1 milliamp. So perfect.
Professor, I have a question.
Yes.
So on the equation for I3, on that loop we have 4 resistors, and you only wrote the 1, 2, 3. Is there a reason why you didn't include the 2 kilo ohms one?
Oh yeah, you're right. So I missed the 2. So there's another 2 here. That's a good catch.
Oh.
So the coefficient for I3, we have 4 resistors. So this is why write it directly like this. It's easier for calculation, but at the same time, it's easy to make mistakes, right? You see that. This is why if you want to be 100% sure you did everything correctly, I still recommend you to count the voltage drop element by element. Yeah, thank you for pointing that out.
No problem.
That's it for this problem. Let's look at the last example. In this example, we're going to use mesh analysis to find a VO in the circuit. In this problem is also different from all the other previous problems. This is a case 4 where it has dependent sources. The way to solve this problem is to treat this source as a regular independent source from the beginning. And then in addition to that, we write an equation about the controlling variable. Step 1, we're going to define the mesh currents. We define the mesh currents like that. Since these current sources are going upward, I want to reverse the direction of my current source to be aligned the same as the information given. So if I define this way, I1 will be equal to Vx over 4, and I2 will be equal to 6 milliamp. So you don't have a negative sign. Define my I2 like this. Last is my I3. The second step is to write the loop equations. So for the first loop, because it has a given current source, which is very easy, that is Vx over 4. And remember, we're going to use kilo ohm, volt, and milliamp as our unit. So this is why this 4,000 I only need to bring 4 there. I put 3 zeros over there to make it a standard unit. We don't need that. So the second mesh, I have a current I2 that is equal to this current is 6 milliamp. I'm not in a hurry to put the units back on. Next loop or the next mesh counts the voltage drop. So if we do it one by one, we will have a 2K times I3 minus I1 plus 4 times I3 plus I3 minus I2 times 4. So we know the coefficient for I3 is simply the summation of all the resistors. So that is 244. And a shared resistor with 2 with I1, so minus 2 times I1. And another shared is this 4 with the current I2, minus 4 I2. That is equal to 0. So now we have 3 equations, but we have 4 unknowns because of this dependent variable. We need an additional equation, and this equation comes from the controlling variable. In this case, the controlling variable is Vx. This current depends on Vx. We need to write a Vx in terms of the mesh currents that we define. So let's find a Vx. Vx is over here. If I write a Vx in terms of all these currents, I will need to write it using Ohm's law. Vx that is equal to the 4K times the current going through this resistor, which is I2 minus I3. That's how we get these 4 different equations. The next step is to solve all these equations. I1 is equal to 3 milliamp. And I3, I get it as a 3 milliamp as well. And Vx is equal to 4 times I3, which is 12 volts. Step 5, draw the conclusion. In this problem, we are looking for VO. So we'll find a VO by using Ohm's law. VO is over here. The current going through this resistor, that is I3. So that is equal to 4 times I3, which is equal to 12 volts.